Hi students, I am Sheeba, EC Department from Emmanuel Research JJ College of Engineering. Today we are learn about the topic optical fiber. First we can see the introduction of communication. The English word communication is derived from the Greek word communicare, which means exchange of information. For as long as humans have been on this planet, we have invented forms of communication, from cave paintings, symbols, smoke signals, carrier beacon, postal system, newspapers, radio, telegraph, telephone, television, internet, email, text message, social media like Facebook, Messenger, WhatsApp, etc. that have constantly evolved how we interact with each other. Technology has redefined communication. People no longer have to wait for years, months, weeks, and days to receive information or message. Today, text, emails, tweets, and personal messages can reach the recipient in just a matter of seconds. We communicate in a finger snap. Now we can send information in forms, audio, video, and data. Next, we can see the fiber optic cable. The fiber optic cable is a light pipe that carry a light beam from one place to another. Light is an electromagnetic signal like a radio wave. It can be modulated by an information signal and sent over the fiber optic cable. The frequency of light is extremely high. It can accommodate wider bandwidth of information, and thus extremely high data rates can be achieved with excellent reliability. The advantages of fiber optic cables are wider bandwidth, lower loss, lightweight, small size, strength, security, interference, immunity, and safety. The disadvantages of fiber optic cable is small size, brittleness, and more difficult to work with. The fiber optics is a branch of optics which deals with the study of propagation of information in the form of light through transparent dielectric optical fibers. Next, we can see the definition of optical fiber. Optical fiber is a thin and transparent hiding dielectric medium or material that hides or transmits information as light waves using the principle of total internal reflection. Optical fiber cable. A bundle of optical fibers consists of thousands of individual fiber wires as thin as human hair, measuring 0.004 mm in diameter, is known as optical fiber cable. Next, the light is a kind of electromagnetic radiation. All kind of electromagnetic wave is made up of both electric and magnetic fields that travel through space from one place to another. Next, we can see the optical fiber structure and construction. The optical fiber dimensions are core diameter 5 micrometer to 600 micrometer, cladding 125 micrometer, diameter 750 micrometer, protective layer 250 micrometer, to 1500 micrometer, 0.1 to 0.5 numerical aperture, 200 to 500 acceptance, and angle bandwidth is 50 megahertz. Next, the principle of optical fiber. An optical fiber works on the principle of total internal reflection. John Tyndall observed that the propagation of light through the optical fiber will be in the form of multiple total internal reflections. The definition of total internal reflection: when a light ray travels from denser medium to rarer medium and the angle of incidence is greater than the critical angle, then the light ray reflects totally. This phenomenon is known as total internal reflection. Normally, the light waves travel in a straight lines. The light waves travel at the speed of light, which is generally considered to be 10^8 meter per second or 186 into 10^3 miles per second in free space. The speed of light depends upon the medium through which the light passes. The reflection of light from a mirror follows a simple physical law which is called as law of reflection. Assume an imaginary line that is perpendicular to the flat mirror surface, which is referred to as the normal. The normal is usually drawn at the point where the mirror reflects the light beam. The angle of incidence. The angle at which the light strikes a surface with respect to the normal is called the angle of incidence. The angle of the incident light ray determines whether the ray will be reflected or refracted. Angle of reflection. The angle at which light is reflected from a surface is called the angle of reflection. Angle of incidence phi1 equal to angle of reflection phi2. Refraction. When waves passes from less dense medium to more dense medium, the wave is refracted towards the normal. Refraction is the bending of a light ray that occurs when the light rays pass from one medium to another. Next, total internal reflection. To consider the propagation of light in an optical fiber, utilizing the ray theory model is necessary to take an account of the refractive index of the dielectric medium. The refractive index of a medium is defined as the ratio of the velocity of the light in a vacuum to the velocity of light in the medium. Partial internal reflection. Let the two media have refractive indexes n1 and n2, where n2 less than n1 and pi1 and pi2 be the angles of incidence and angles of refraction respectively, where pi2 is greater than pi1. It is observed that a small amount of light is reflected back into the originating dielectric medium, that is partial internal reflection. Next, we can see the principle of optical fiber. is the derivation of critical angle. Next, the conditions for total internal reflection is: first one, the light ray should move from denser to a rarer medium. When I less than theta c, then the light ray refracts into a rarer medium. When I equal to theta c, then the refracted light ray passes along the interface of the two media. When I greater than theta c, then the light ray is reflected back into the denser medium and we get total internal reflection. Next, the acceptance angle and acceptance cone. The maximum angle at which the light can suffer total internal reflection is called as acceptance angle. The acceptance cone is derived by rotating the acceptance angle about the fiber optics. Figure shows the light ray incident on the fiber core at an angle which is the maximum angle to the axis at which light may enter the fiber in order to be propagated, and is often referred to as the acceptance angle for the fiber. It may be observed that this ray is refracted at the air core interface before transmission to the core cladding interface at the critical angle. Any rays which are incident into the fiber core at an angle greater than theta a will be transmitted to the core cladding interface at an angle less than the critical angle pi c, and will not be totally internally reflected. It is refracted into cladding and eventually lost by radiation. Consider the ray enters the fiber from a medium of refractive index n0 and the fiber core has a refractive index n1 which is slightly greater than the cladding refractive index n2. By applying Snell's law to external incidence angle, n0 sin theta a equal to n1 sin theta 2. Then acceptance angle theta a equal to sin inverse root of n square minus n2 square. Next, the numerical aperture. Numerical aperture represents the light gathering power of an optical fiber. It is a measure of the amount of light that can be accepted by a fiber. The value of Na ranges from 0.13 to 0.50. Numerical aperture is proportional to the acceptance angle. So, numerical aperture is equal to the sine of the acceptance angle. Types of optical fibers. Optical fibers are classified into two major categories based on: first one, number of modes transmitted into the optical fibers, and the second one, refractive index profile of the fibers. According to the mode of propagation, optical fiber is classified into two. First one, single mode and multi-mode optical fibers. Multimode optical fiber is divided into two: step index optical fiber and graded index optical fiber. First one, single mode optical fiber. In single mode, light follows a single path through the core. If the optical fiber which allows one mode of light propagation, then it is known as single mode optical fiber, because it has very small core diameter so that it can allow only one mode of light propagation, as shown in figure. In general, single mode optical fibers are step index optical fibers. They are made from doped silica with mixtures of metal oxides. The ray travels along the axis of the fiber. Next, we can see the single mode optical fiber dimensions. Core diameter is 5 micrometer to 10 micrometer. Cladding around 125 micrometer. Diameter 250 micrometer to 1000 micrometer. Protective layer numerical aperture 0.08 to 0.10. Then the acceptance angle more than angle of cladding. The advantages of single mode fiber is no intermodal dispersion. Information capacity of single mode fiber is large. The disadvantages of single mode fiber: launching of light into single mode and joining of two fibers are very difficult. Fabrication is very difficult and hence the fiber is so costly. Next, the multi-mode fiber. In multi-mode, the light takes many paths through the core. The number of paths possible for a multi-mode fiber cable depends on the frequency of the light signal, the refractive indexes of the core and cladding, and the core diameter. Mathematically, the number of propagation of modes is in multi-mode fiber is expressed as n into pi d by lambda root of n1 square minus n2 square the whole square, where d core diameter, lambda wavelength, n1 refractive index of core and n2 refractive index of cladding. The advantages of multi-mode fiber is the larger core radially as well as numerical aperture of the multi-mode fibers make it easier to launch optical fiber into the fiber. Connecting together of similar fibers are easy. Light can be launched into multi-mode fiber using light emitting diode, although LEDs have less optical output power than laser diodes. LEDs are easier to make and less expensive and have longer lifetimes. Fabrication is less difficult and so fiber is not costly. The tolerance requirements of this fiber is also low. The disadvantages of multimode fiber is intermodal dispersion or intermodal distortion. When an optical pulse is launched into a fiber, the optical fiber in the pulse is distributed over the modes of the fiber. Each of the modes that can propagate in a multimode fiber travels at a slightly different velocity. So the optical pulses arrive at the fiber end at slightly different times, thus causing the pulse to spread out in time as it travels along the fiber. An intermodal dispersion in a fiber can be reduced by using a graded index profile in a fiber core. This allows fibers to have much larger bandwidth than the step index fibers. Even higher bandwidth are possible in single mode fibers where intermodal dispersion effects are not present. Multimode optical fibers. The core diameter is very large compared to single mode fibers, so that it can allow many modes of light propagation, and hence it is called multimode optical fiber. The multimode optical fibers are useful manufacturing both for step index and graded index optical fiber. They are made by multi-component glass compounds such as glass-clad silica, silica-clad silica, doped silica, etc. The core diameter of multimode optical fiber is 50 micrometer to 350 micrometer. Depending on the refractive index profile of fiber and modes of fiber, three configurations are commonly used. These optic fiber configurations are given as: first one, single mode step index fiber; second one, multi-mode step index fiber; third one, multi-mode graded index fiber. First one, single mode or mono mode step index fiber. Single mode step index fibers are the dominant fibers used in today's telecommunications and data networking industries. A single mode step index fiber has a central core that is significantly smaller in diameter than any of the multimode cables, with a typical core size of 8 to 12 micrometer. In fact, as the diameter is sufficiently small, there is essentially only one path that light may take as it propagates down that cable. The advantages of single mode step index fiber is low intermodal dispersion, which is due to one mode propagation. For very long distance transmission and maximum information content, this cable should be used. Second one, multi-mode step index fiber. Multi-mode step index are similar to the single mode step index, except the diameter of the center core, which is much larger with the multi-mode configuration. It is easy to manufacture. Its core diameter is varying from 50 to 200 micrometer, and the cladding is from 125 to 400 micrometer. The light rays are propagated down the core in a zigzag manner. There are many paths that a light ray may follow during the propagation. Multimode step index fiber allow the propagation of a finite number of guided modes along the channel. Normalized frequency. The normalized frequency is used to determine the number of modes a fiber can support. The total number of guided modes or mode volume M for a step index fiber is related to the V value of the fiber by the approximate expression M approximate V square by 2. In multi-mode step index fiber, the considerable dispersion may occur due to the differing group velocities of the propagation modes. Third one, multi-mode graded index fiber. Graded index fiber are categorized by a central core with a non-uniform refractive index. Multi-mode graded index fiber cables have several modes or paths of transmission through the cable, but they are much more orderly and predictable. The index of refraction are varying continuously across the core, and the light rays are bent smoothly and converge repeatedly at points along the cable. The light rays near the edge of the core take a longer path but travel faster since the index of refraction is lower. All the modes of our light path tend to arrive at one point simultaneously. The result is that there is less model dispersion. These fibers are easier to couple the light into and out of the fiber than the single index fibers, but are most difficult than multi-mode step index fibers. The core diameter is very large compared to single mode fibers, so that it can allow many modes of light propagation, and hence it is called multi-mode optical fiber. Figure shows the multi-mode step index fiber, and the next figure shows the multi-mode graded index fiber. Applications. Because of its less bandwidth, they are used in short call communication systems. A local area network is a computer network that interconnects computers in a limited area, such as a home, school, computer laboratory, or office building, using network media. The advantages of fibers are launching of light is easy, connecting to fibers is easy, fabrication is easy, cost is low. Figure shows the multi-mode step index optical fiber. Figure shows the single mode step index optical fiber. Figure shows the graded index optical fiber. In intermodal dispersion, when more than one mode is propagating through a fiber, then the intermodal dispersion will occur. Since many modes are propagating, they will have different wavelength and will take different time to propagate through the fiber. This results in elongation or stretching of data intervals. This is known as intermodal dispersion. Next, we can see the optical fiber communication system. The basic components in the optical fiber communication are the light source, the optical transmitter, the optical fiber, and the optical receiver. Additional elements used in optical link are fiber and cable splices, connectors, regenerators, beam splitters, and optical amplifiers. First, we can see the information source. The information signal to be transmitted may be voice, video, or computer data. The first step is to convert the information signal into a form compatible with the communication medium. In optical communication, the information source provides an electrical signal as an input signal to the transmitter. If it is a non-electrical signal, then the transducer is used in the optical transmitter that converts the non-electrical signal into an electrical signal. Next, transmitter. Transmitter contains the following components: drive circuit and light source. Drive circuit. The drive circuit is used to drive the electrical signal into the light source. Next, the light source. The light source has two main functions as it generates the optical signal. It modulates the information signal by using the optical signal as a carrier signal, which is used for propagating the information signal to a long distance. The electric input signals to the transmitter can be either an analog or of a digital form. The transmitter circuitry converts these electrical signals to an optical signal by varying the current flow through the light source. The optical source which provides the electrical optical conversion may be either a semiconductor laser or light emitting diode. Third one, information channel. The information channel is a medium which is used for bridging the distance between transmitter and receiver. In fiber optic communications, the fiber optic cables are used as channels. Fiber optic cables are made from glass and plastic. Glass has the lowest loss but is brittle. Plastic is cheaper and more flexible but has high attenuation. For the long distance optical communication, we use repeaters to compensate the attenuation loss. Repeaters. The repeater contains optical receiver, optical transmitter, and amplifier. Optical receiver. An optical receiver detects the optical signal and converts it into an electrical signal which is amplified, reshaped, and sent to the electric input of the amplifier. Amplifier. The amplifier receives the electrical signal from the optical receiver and amplifies the signal and also send it into optical transmitter. Optical transmitter. An optical transmitter converts the electrical signal back to an optical signal and sends it down the optical fiber waveguide. Receiver. The receiver consists of a detector that will detect the optical signal and convert them into an electrical current. The electrical current developed by the detector is proportional to the power in the incident optical signal. The detector output current contains the transmitted information. Photodiodes and in some instances phototransistors and photoconductors are utilized for the detection of the signal and the optical electrical conversion. The electrical signal is then amplified and restores it to its original form before passing it on to the signal destination. Next, the advantages of optical fiber. Optical fibers have largely replaced copper wire communications in core networks in the developed world because of its advantages over electrical transmission. Here are the main advantages of fiber optic transmission. Safety. The fiber is non-conducting and is therefore safe in all environments. It uses light waves for communication, hence it is shock-proof. Since it is shock-proof, it is very useful in sensitive areas like petroleum industries, oil and natural gas industries, cotton industries, etc. Weight. Fiber optic cables are made of glass or plastic and they are thinner than copper cables. These make them lighter weight and easy to install. Low power loss. An optical fiber offers low power loss which allows for longer transmission distances than comparison to copper cable. Next, the bandwidth of fiber optic cable. Fiber optic cables have a much greater bandwidth than metal cables. The amount of information that can be transmitted from unit time of fiber over other transmission media is far greater than copper cables. The security of fiber optic cables, it cannot be tapped unlike copper cables. There is no leakage of signals, so communication is secured. It is very strong, flexible and can work on high temperature. It does not have corrosion due to water, chemicals and high humidity, etc. It is cost effective and maintenance free. It is very easy to install. It does not require labor. Next, the losses in fiber optics. Attenuation, dispersion, intermodal, intramodal, bending loss, macro scattering losses, linear, non-linear absorption, intrinsic, extrinsic coupling. Attenuation. Attenuation means loss of light energy as the light pulse travels from one end of the cable to the other. It is also called signal loss or fiber loss. It also decides the number of repeaters required between transmitter and receiver. Attenuation is directly proportional to the length of the cable. Attenuation is defined as the ratio of optical output power to the input power in the fiber of is attenuation constant. The various losses in the cable are due to absorption, scattering, dispersion, bending. Bending losses. The loss which exists when an optical fiber undergoes bending is called bending losses. There are two types of bending: macroscopic bending, bending in which complete fiber undergoes bends which causes certain modes not to be reflected and therefore causes loss to the cladding. Microscopic bending. Either the core or cladding undergoes slight bends at its surface. It causes light to be reflected at angles when there is no further reflection. Figure shows the macroscopic bending and microscopic bending. Next, the absorption loss. Absorption of light energy due to heating of ion impurities results in dimming of light at the end of the fiber. Two types of absorption loss: intrinsic absorption, extrinsic absorption. Intrinsic absorption caused by the interaction with one or more components of the glass occurs when photon interacts with an electron in the valence band and excites it to a higher energy level near the UV region. Eccentric absorption, also called impurity absorption, it results from the presence of transition metal ions like iron, chromium, cobalt, copper, and from OH ions, that is from water. Dispersion loss. As an optical signal travels along the fiber, it becomes increasingly distorted. This distortion is a sequence of intermodal and intramodal dispersion. Two types of dispersion loss: intermodal dispersion, intramodal dispersion. Intermodal dispersion, pulse broadening due to intermodal dispersion, results from the propagation delay difference between modes within a multi-mode fiber. Intramodal dispersion, it is the pulse spreading that occurs within a single mode. Material dispersion is a waveguide dispersion. Next, scattering losses. It occurs due to microscopic variations in the material density, compositional fluctuations, structural inhomogeneities, and manufacturing defects. Coupling losses. The mechanical losses due to the coupling of optical fiber cables is called coupling losses. Now we are conclude the section optical fiber communication. Thank you.